All right, today we're going to talk about vectors in the plane and also navigation. Unit vectors. A unit vector u which has a length of 1 and the same direction as a given non-zero vector v is going to be this formula right here. So u is a scalar multiple of v, so we say the unit vector is equal to the vector v divided by its magnitude. Or you could also write that as 1 over the magnitude times the vector. So that is the formula for a unit vector. So we're going to use that to help us. So unit vector means, again, the magnitude is a length of 1. So this example says find the unit vector u with the same direction as the vector of v, which has components of 3, 4. So if we draw a little picture here, our components are horizontal component of 3 and our vertical component is 4. So we know that if we want to find the magnitude of vector v, it's using the Pythagorean theorem. So the square root of 3 squared plus 4 squared is 9 plus 16, which gives us 25, and the square root of 25 is 5. So then to find our unit vector, we're going to do 1 over the magnitude times our horizontal and vertical component. So this gives us then 3/5, 4/5. So this would be the component form of vector u. So even just to check, you can see that for this one, the magnitude of vector u would be the square root of 3/5 squared plus 4/5 squared. So when we do that, we get the square root of 9 over 25 plus 16 over 25. And notice that gives us the square root of 16 plus 9 is 25 over 25, which is just the square root of 1, and that equals 1. So that's the magnitude. And the direction would be also the same. Standard unit vectors I and j are positioned along the x and y axis and defined as I is 1, 0, and j is 0, 1. Any vector v with horizontal component A and vertical component B can be written in the form of AI plus AJ. This is called a linear combination of vectors I and j. And so just to show you what we're really doing, so we're splitting vector v up, and so we could write it as vector or the components of a comma 0 plus 0 comma b, and then when you multiply it by the components for I and j, you would get a times 1, 0 plus b times 1, 0, and 1, 0 is I and 0, 1 is j, so that's why we can write it in this form right here. So if it says put it in a linear combination form, that's what you're doing. So these examples say write each vector as a linear combination of I and j. So vector v would be equal to 2i plus 5j. And why is that? Because we can write this as 2, 0 plus 5, 0, which then gives us 2 times 1, 0 plus 5 times, oops, I read that backwards. Yes, I did, sorry. 0, 5. There we go. So 5 times 0, 1, there we go, that's better. And so then that gives us 2i plus 5j. But it's not necessarily necessary to write all that work, so you can just write it in this form from the horizontal, from the component form. So RS with R being -9, 8, and S being -5, 6. So first we're going to want to find the component form of RS. So remember, component form means you're subtracting, in this case, the terminal minus the initial. So terminal is S and initial is R. So this would be -5 minus -9 and -6 minus 8. So when you subtract 5 minus -9 is -5 plus 9, so that gives us 4, and this would be -14. So then the component form for RS would be 4I minus 14J. So next it says find the component form of vector v, which is equal to 2u minus 2w, given that u is 2I minus j and w is I plus 2j. So vector v would then be equal to, so we have 2 times u, so 2 times 2I minus j, and then minus 2 times w, which is I plus 2j. So you could put these in component form first if you wanted to, or you can do this form and multiply it out, combine like terms, and then put it in component form. It doesn't matter, so I'll show you in just a minute. So right here, then if you distribute, we get 4I minus 2j minus 2I minus 4j. And then you can see we have our like terms. So that gives us 2I, and then we have minus 6j. But of course, this is not the correct form because this is linear combination form. So then we would rewrite this as vector v is equal to 2 comma -6, which is the component form. And again, you could have converted these in the beginning. So this would be 2 comma -1 in component form, and this would be 1 comma 2. And then you could do the operations. All right, next is trigonometric forms of a unit vector. So if u is a unit vector, remember that means the length of 1 for the magnitude, then the terminal point of u lies on the unit circle. And so therefore, u, or vector u, is equal to the components of a comma b can be written as vector u is equal to the cosine of theta, comma, the sine of theta, just like from our unit circle. Because remember, if we were to draw a line going down, make a right angle here, this distance is a, this is b, and we learned that when we did our unit circle that the x-coordinate was for cosine and the y-coordinate is for sine. And so we're kind of using that same idea here. And so we could also write this as a linear combination, which would be equal to cosine theta I plus sine theta j. So given the magnitude and the angle theta, find the component form for v. So, and it's saying that v is equal to a comma b in component form, or in linear combination form, ai plus bj. So for this one, we're going over a distance of a and up a distance of b. So to solve for a, we would need to know, if we're given theta and the magnitude, we know then the a is the adjacent and the magnitude is the hypotenuse. So the cosine of the given angle theta is equal to the adjacent over the hypotenuse, which is the magnitude. So that means to solve for a, we multiply both sides by the magnitude. So a equals the magnitude of the vector times the cosine of the given angle, because again it says given the magnitude and the angle, we're looking to solve for a, and now we're going to solve for the vertical component, which is b. So this one's the opposite, and we have the hypotenuse. We're going to use sine. So the sine of the given angle equals b over the magnitude, which is also given. So that means b is equal to the magnitude of v times the sine of theta. So then for the next one, if we wanted to write this in the component form, this would be the magnitude of the cosine of the angle, comma, the magnitude times the sine of the angle. This should look familiar. We did this when we converted our polar points. So remember, we took r times the cosine of theta and r times the sine of theta. Well, it's the same idea here. Remember, theta is the direction angle of vector v. So direction angles we've already talked about before. So remember, direction, the angle theta represents the direction of vector in the plane that's that is the standard angle from the positive x-axis to the vector when it's in standard position. So remember, if this is x and y instead of a and b, so this would be over x and up y. So to solve for the angle, we're using the opposite and the adjacent because that's what's given. So that would be the tangent then. So the tangent of theta equals y over x. And just remember, tangent is sine over cosine. So you could also say the magnitude of the sine of theta over the magnitude of the cosine theta, because remember we said that that was the horizontal or vertical, excuse me, horizontal component, and this one's the vertical component. So that's another way to kind of think about that. All right, so next it says find the magnitude and direction angle of the vector 12i plus 15j. So if I want to find the magnitude and the direction angle, the first thing I like to do is think about what quadrant this is in. So positive and positive means we're in quadrant 1. So we're going over 12 and up 15. So we're looking for the magnitude of vector v and the direction angle. So we've already been doing this. So the magnitude of the vector is equal to the square root of 12 squared plus 15 squared, which gives us the square root of 369, and that breaks down into 9 times 41. So that gives us 3 root 41. And so then for the direction, we have 15 and 12. So 15 is the opposite, 12 is the adjacent, so we're using the tangent. So the tangent of theta equals 15 over 12. And so then because we're in quadrant 1, when we do the tangent inverse of this, so the tangent inverse of 15 over 12, we're going to make sure our calculator is in degree mode. So if I go to mode, it's in degree mode. So we want to take the tangent, tangent inverse, 15 divided by 12, which gives us 51.3 degrees. And remember, we have to be careful of what quadrant we're in, because if we were in quadrants 2 or 3, we would want to add 180 degrees to the answer, because remember, inverse answers only give us results that are answers, solutions that are in quadrant 1 and 4 because of the inverse rules. So the next one says, find the component form of vector v given that v is equal to, magnitude v is 3 and v is in the direction of negative 3i minus 4j. So let's go ahead and think about this one. So if we know that we're going the direction of negative 3 and negative 4, so that means we're in quadrant 3. So I'm going to go ahead and draw my vector. So this would be negative 3 for the horizontal component, and the vertical component is negative 4. So this would be theta. And it's saying that the magnitude is 3, but we're in the same direction as this. So let's go ahead and find the direction first. So then the tangent of theta is equal to negative 4 divided by negative 3, which of course is just 4/3. So theta equals the tangent inverse of 4/3, which gives us theta equals 51.1 degrees if we round to the nearest 10th. But remember that 51.1 degrees is in quadrant 1, and this is supposed to be in the direction of quadrant 3. So we have to add 180 degrees to that answer to get the correct quadrant. So theta is equal to 233.1 degrees. All right, so that gives us the direction, and we also have the magnitude. So the magnitude is 3. So if we draw another picture, we know the direction angle, and we know the magnitude is 3. And so if we want to find the component form, remember we said that the component form would be equal to the magnitude of the vector times the cosine of the angle and the magnitude of the vector times the sine of the angle. So in this case, we have the magnitude, which is 3, times the cosine of 233.1 degrees, comma, 3 times the sine of 233.1 degrees. And then we can go ahead and plug this into our calculator. So 3 times the cosine of 233.1 and 3 times the sine of 233.1. So this gives us the component form of negative 1.8 and to negative 2.4. And then of course you can check to make sure that makes sense, because again, the direction angle was in quadrant 3, so the direction, these are both negative for the horizontal and the vertical component. Next one says find the component form of vector u given the following. The magnitude is 35 and the direction of angle u is 125 degrees. So 125 degrees, of course, is quadrant 2. So that would be something like this. And this is 35. So for this one, here's our angle. We're using, again, 125 degrees. So for this one, vector u's component form would be equal to the magnitude of vector u times the cosine of the angle and the magnitude of vector u times the sine of the angle. So 35 times the cosine of 125 and 35 times the sine of 125 degrees. So this gives us 35 times the cosine of 125, so negative 20.07, so negative 20.1, and 35 times the sine of 125 gives us 28.7. And that would be the component form. All right, so now we're going to look at navigation and applications. Angles have different ways of being measured. Standard position is measured from the positive x-axis with positive angles opening counterclockwise. The course of a ship or a plane is the angle measured clockwise from the north direction to the direction of the ship or plane. This is called course, is called a bearing. Bearing, true bearing, or compass bearing, those all mean the same thing, or direction angles given as rotations measured from clockwise to north. We also have quadrantal bearings, which is something we're going to talk about down here. So for this, it says convert the bearing of 220 degrees to a standard angle, and then draw the angle in standard position. So notice that north is 0 degrees, so north, east, south, and west. So north is 0 and east is 90. South is 180 and west is 270 degrees. But when we're talking about the standard angle, that starts here at 0 degrees. This would be 90 degrees, 180 degrees, 270 degrees, and all the way around is 360 degrees. So we're trying to figure out what this angle measurement would be in standard position. So there's a couple different things we could do. We could find the reference angle. We could also notice that the difference between these angles is that 90 degrees. So I'm going to do it one way first, and then I'll look at the next way. So let's say we were to take off this 90 degrees here. So we have 220 minus 90. So if we do 220 minus 90, notice we get 130. So that would be the distance from a standard angle from here to here as a negative angle measurement. So from here to here is negative 130 degrees. So if we want the positive angle, then we use our coterminal angles to find that. So 360 degrees, and then we take that 130 and subtract it. So 360 minus 130, notice it gives us 230 degrees. That's just one way to figure out what the standard angle measure is. We could also use, like I said, reference angles. So if instead I wanted to use a reference angle, remember the reference angle is the positive acute angle made by the terminal side and the shortest angular distance to the x-axis. So this would be the reference angle here, which I'll call theta prime. So if I know from here to here is 220 and all the way to here is 270, well, I could do 270 minus 220, which gives me a reference angle of 50 degrees. So if I know that's 50 degrees, that's this measurement from here to here, then I could do 180 plus that 50, and notice I get 230. So it gets you the same answer in the end, it's just a different way of going about it. Could I have instead figured out what the measure from here to here was? Sure. Normally I don't do that side because usually we always use the x-axis because it's a reference angle, but if we did this side here, that would be then 40 degrees. So then you could do 270 minus the 40 and you would get 230. So a lot of different ways of looking at these problems, and again, just use kind of what works for you. So if you like to use the reference angles, you can use the reference angles, or you could think about it the first way that we did the problem, first figuring out that the negative angle measurement from here to here is negative 130, and then adding the 360 to that. So let's look at a bearing of 160 degrees. So we're going to go ahead and sketch this first. 160 degrees would be in quadrant 4. Because remember, this is north 0, 90, 180, 270. So it would be down here, quadrant 4. So that would be the bearing of 160 degrees. So again, the difference between this and drawing our angle in standard position is that extra 90 degrees that we have. So we could think about taking this 90 degrees off. So 160 minus 90 tells me that this measurement from here to here is 70 degrees, or if you wanted to think about it like a negative angle, it'd be negative 70 degrees. So if we took 360 minus that 70 degrees, notice we get 290 degrees, which would be all the way around. So again, first I took 160 degrees minus 90 degrees to get the 70 degrees, and then 360 degrees minus the 70 degrees. And that's also the reference angle in this case is the 70 degrees. So again, that's this angle here is negative 70 degrees. So you again think about it like coterminal angles. 360 plus negative 70 gives us 290. Looking at the next one, we have a bearing of 335 degrees. So 335 degrees is going to be in the second quadrant because it's in between 270 and all the way around back to north would be 360. So that's going to be somewhere up here. So all the way around to there. So if we want to figure out what this angle is in standard position from here to here, again, notice that the difference is that 90 degrees here. So we could figure out the negative angle measurement and then add 360 to that. So from here to here is going to be equal to, if we go, so take the 90, so 335 degrees minus the 90 degrees, which gives us 245. So that means this would be a negative angle measurement of 245 degrees. So if we want the coterminal angle, remember coterminal angles, you add and subtract 360. So 245 degrees plus 360 degrees is equal to 115 degrees. Of course, that's not the only way we could have solved for this. If we wanted to find the reference angle would be this angle right here because it's a positive acute angle made with the terminal side and the shortest angular distance to the x-axis. So if we wanted to find that angle, we could take the 335 and subtract it from 270, which means that this angle from here to here as a reference angle is equal to 65 degrees. So then we could have taken on our standard angles from 180 is to here, remember, so 180 minus then the 65 gives us 115. So that's another way to look at it. Also, we could have figured out what this angle measurement is here. So if we took 90 minus that 65, we can see that that's 25 degrees. So if we took then 90 plus 25, again, notice you get 115. So these are all just different ways of finding that standard angle measurement, which again was 115 degrees. So just use what works for you. So if we have a bearing of 36 degrees, again, bearings from north going clockwise, that would be going this direction. So then if I wanted the standard angle measurement, then I'm trying to figure out from 0 going this direction what that standard angle measurement is. So if we take 90 degrees minus 36 degrees, we get 54 degrees for the standard angle. So with the exception of quadrant 1, an easy way to think about this is what do we do each time? So we had that extra 90 degrees, right, that we had to subtract. And also we then found the coterminal angle by either adding by taking 360 and subtracting the angle or adding it. So, whoops. And so here's a little trick. You could do 450 degrees minus the bearing to get the standard angle. And again, you don't need to do that in the first quadrant. If you're given angles acute, it's just 90 minus that. But if it's in the other quadrant, so just to show you up here, so again, we first subtracted the 90 and then we did the coterminal angle. So if I take 450 and subtract 220, notice I get 230. So just another way of looking at it. So same thing with the next example, 450 minus 160 gives me 290. And over here, if I were to take 450 minus 335 degrees, I would get 115 degrees. And again, that's because we subtracted the 90 and then found the coterminal angle. So for this one, again, you wouldn't want to do that because it's 36 degrees, because if you did 450 minus 36, you just have to subtract 360 again. So it's just doing more work than just taking the 90. So then those are all, of course, coterminal angles, but we only need from here to here. So let's go ahead and look at the directional bearing, which is also called quadrant bearing. Directions are angles given as a starting direction, either north-south, and then an acute angle of rotation measured towards the second direction, either east or west. And sometimes people write them the other way as well, so you just have to be kind of careful of how you're looking at it. So for this first one, it says a bearing of north and then 20 degrees to the east. So that means, again, you would start from north and you would go east 20 degrees. So if I want the standard angle, that would be from here to here. So the standard angle, we would take 90 degrees minus 20 degrees, and that gives us 70 degrees for standard position. Then for this one, it says a bearing of south 41 degrees east. So here's south, and we're going 41 degrees towards the east, so that would be here. So basically, we need to figure out our standard angle measurement so we can find out what this angle measurement is. So if I take 90 degrees minus 41 degrees, I get 49 degrees. So this would be negative 49 degrees if you want to think about it as a standard angle. So we're using 49 degrees as a reference angle, which is a positive acute angle. So if that's 49 degrees, remember then all the way around from here to here would be then 360 minus that 49, which gives me 311 degrees. For the standard position. So we're going to do the same with these. Sketch the angle given in bearing and then determine the angle measure in standard position. That's coterminal. So we have a bearing of north 60 degrees west. So north is at the top, and we're going 60 degrees to the west. So that would be this direction. So that means I want to figure out the standard angle from here to here. So that means we need to add 90 degrees to 60. So 90 degrees plus the 60 degrees is going to give me my standard angle of 150 degrees. If you wanted to use reference angles, you know that this reference angle from here to here would be 30 degrees. So you could also do 180 degrees minus 30 degrees, which gives you 150 degrees. That would also work. If we have a bearing of south 11 degrees west, that would be here. And then, so in standard position, we're going all the way around to here. So I could do, I know from all the way around here is 270. So I could take 270 and subtract 11, and I get 259. So that would work. That's one way to do the problem. Or I could figure out the reference angle. So we know if that's 11 degrees, then 90 minus 11 means the reference angle is 79 degrees. So then I could do 180 plus 79 and also get 259. And why are we doing this? Because when we are going to do application problems, we need to have the standard angle in order to use our calculator to calculate these measurements that we are going to have. And so that's all for today. And then tomorrow we're going to work on the applications.